Good morning, everyone, and welcome to our next presentation, our live presentation of the week for our Your Universe series. Today, we are welcoming a guest speaker, Dr. Dain Kavars, to teach us all about Uranus and Neptune, the planets we have been exploring this week. They are, of course, the seventh and eighth planets from the sun. Well, I'm Dana Thompson. I'm the director of the Brown Planetarium at Ball State University, where we have the largest planetarium in Indiana, where we can recreate the sky. And we wish we were giving this presentation inside our planetarium, but we're bringing you the next best thing with our live experience today. You can still ask us questions and put comments in the chat, and we will get those answered. And we have Rachel Williamson, our planetarium show specialist, to help us do that. But today we are welcoming Dr. Kavars, who has taught solar system astronomy and galactic astronomy classes at the Indiana Academy of Science, Mathematics, and Humanities, located on the campus of Ball State here in Muncie. And he is now entering a new role at the Academy of Interim Executive Director. So we're really excited to have Dr. Kavars help us understand a little bit more about the weather on Uranus and Neptune today. So I'm going to go ahead and turn it over to Dain here for his presentation. And again, I'm going to go ahead and stop sharing my screen and let Dain turn on his video, unmute himself, and you can go ahead and start sharing your screen, Dain. And if you do have a question or a comment, put it in the chat. We'll get it answered. But Dain, go ahead and take it away.
Yes, thank you, Dana. I'm really excited to be here today. I mean, anytime that I get a chance to talk about astronomy, share the things that I know about the planets in the solar system, as is the case today. I mean, it's always a good day when I have the opportunity to do that. And as Dana said, my name is Dain Kavars. I'm the interim executive director at the Indiana Academy for Science, Mathematics, and Humanities. This is a residential school for gifted 11th and 12th grade students in high school that's located right here on the campus of Ball State University. So if you're ever on campus and you're visiting the planetarium, which is a fantastic planetarium on Ball State's campus, stop by the academy, say hi. We can answer questions. Be happy to see you there. So what I kind of want to talk about a little bit here is the last planets in our solar system. We have the seventh and eighth planets, Uranus and Neptune. And I know that you've had a little bit about these two planets earlier this week in those sessions. So I know that a little bit of what I might say here might be some review, but our focus today is going to be on the weather systems of these two planets. And please, I know that Dana said it a little bit ago, but if you've got a question that you have, put that in the chat. She'll interrupt me here. I'm happy to answer questions that you might have at any time in this presentation. You do not have to wait until the very end to ask those. So if there's something that you're seeing on a slide, you've got a question about it, go ahead, type that right in there, and she'll ask that question for me. To me, and I'll do my best to answer it. So we have the last two planets in our solar system. We have Uranus and then we have Neptune. And just looking at the images that you see right here with Uranus on the left and Neptune on the right, you have two planets that look very different from the other planets in the solar system. They even look very different from the two other gas giants in the solar system, Jupiter and Saturn. Both of these planets have a very nice blue color that has to do with the composition in their atmosphere that we'll get to here in a little bit. Uranus is more of a pale blue. Neptune, I love the color of Neptune, that very nice, darker blue. You've got some of even with the darker blue, you got some of that darker blue is even darker blue, and some lighter blue. And it just strikes me as just this beautiful planet in any sort of image. And I'll have some more of those here in a little bit. But when it comes to weather, I have a pretty good idea of what weather is just on my daily experiences of going outside. The same is true for you. You go outside or you look outside and you know that some days it's hot and sunny. Other days it might be cold. There might be snow on the ground, depending on where you live. It might be raining. It might be really windy. Right now, on July 3rd here in the summer of Indiana, I can look out the window and it's bright and sunny. It's really hot out there. It's supposed to hit the low to mid 90s today. To me, that's not pleasant weather. I'll go outside a little bit later and I'll start complaining about it because this is not the weather that I like. It's the weather that when I look out my window, my tomato plants love it, but it is not my type of weather. But we have a good idea of weather on Earth just from our experiences. But how are Uranus and Neptune different? So, here's an image of Earth from above. And this image shows all sorts of clouds. I mean, North America right now is covered in clouds in this image. South America too. There's some swirly patterns and some things like that. If you Google images of Earth, you'll find some that will show hurricane, storm type systems, which are always really cool to see. But typically when we look at Earth from above, you have areas that you can see all the way down to the surface. The land, I can see Mexico on here pretty well. I can see Chile and parts of Argentina down in the south. In some areas I can't because of the clouds. Another example of weather on Earth with these lightning storms that you see, particularly in the Midwest, coming in, usually from the westerly direction, are nice to watch until they get to us. Again, we have a really good idea of weather on Earth, but what about some of these other planets, including the last two planets, Uranus and Neptune? So let's start with Uranus. On the left is that pale blue image that's very common. This is an image taken by the Voyager 2 spacecraft that flew by Uranus back in the mid 1980s. And it doesn't really show a lot. I mean, it's kind of a boring image. It gives you the impression that there's not much going on in the atmosphere of Uranus. But that's not true at all. There are actually some very, very exciting things that are taking place. If you look on the right, we have an image of Uranus in infrared. Now, infrared is a different type of light that we need a different type of telescope to observe. So with my eyes, I can see visible lights. I can see the colors in the spectrum from red to blue. Infrared is a good example of infrared is your own body. You right now are giving off body heat, and that's in the form of infrared radiation. And if you had an infrared camera pointed at you, that camera would pick up the outline of your body based on the heat signature that you're giving off. Uranus and the other planets do the same. And so when we look at Uranus in infrared, we see a planet that looks very, very different. One, you see a very thin ring structure. And I think you talked about that in a previous session, so we won't go into that in any more detail, but that's an interesting thing that you can't see otherwise. The sort of atmospheric surface of Uranus looks different too. There are these sort of bands that go across if you look at the image closely. And you'll see on here that the left side is coming out looking a little bit different than the right side on the image. And we'll talk about that a little bit later as we get into seasons here. And then if you look close, you've got some of these interesting little circular features, call them splotches if you want. Well, that's where we're starting to look at some of the weather systems that we have on what we are calling a surface of Uranus. There's no real sort of surface like Earth because Uranus is not a rocky planet like Earth, but we see some interesting things that are going on in the atmosphere. And just zooming in a little bit more, we can see this a bit better, same image. Again, we see these kind of splotches in here. And so these are some of our what could be storm type systems, not necessarily storms like we have on Earth that are raining down water or anything like that, but there's circulation patterns that are in the atmosphere, or the rising of gas in some areas, the falling of gas. This is weather taking place in the atmosphere of this planet. A few facts. And we'll make some comparisons here to Earth because that's where things get really interesting. So temperature. Think about the coldest temperature that you have on Earth. So, here in Indiana in the winter, we may have days that get down to 0 degrees Fahrenheit, 10 degrees Fahrenheit. Those are pretty cold winter days in Indiana. And sometimes the temperature will get below 0 Fahrenheit. Sometimes a wind chill every once in a while will get us -10, -20 degrees below 0. We know that water freezes at 32 degrees Fahrenheit, but look at the temperatures here for Uranus. So we're looking at temperatures of negative 365 degrees Fahrenheit. That is cold. If we're thinking wind chills of 10 to 20 below 0 are cold, think about -365. That is definitely cold. You need your hat, you need your scarf, you need your coat. You probably need 30 hats. I mean, very, 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 very cold, and far colder than any place that has ever had the coldest temperature on Earth. So think about the poles. Temperature on Uranus is way colder than that. Wind speeds. I think it gets windy when it's 20 miles per hour, and there's no trees blocking the winds. I can have shingles. I've had shingles rip off my roof when there's been gusts of winds that will hit 50, 60 miles an hour. Hurricanes on Earth, 100, 110, 120 miles per hour. Here on Uranus in the atmosphere, we have over 500 miles per hour, 500 to 600 miles per hour. That's a windy day. So some characteristics with the weather that are very, very, very different from Earth. Now, seasons, right? We know we have seasons on Earth. We have summer right now, then we're going to go into fall, then it'll get colder, it'll be winter, then we go into spring, and then we start back over with summer, and we just repeat that every year. Well, Uranus has seasons too, and it has to do with the side of Uranus that is pointed toward the sun. Whichever side is getting more energy from the sun is going to have a slightly warmer temperature, giving us a summer, so to speak. The opposite side giving us a winter. Uranus is interesting because it's tipped on its side. So if I go back into this image right here, where you have these rings that are kind of up and down, remember when you were watching the videos for Saturn, Saturn's rings were kind of across like that, as you might expect. So Uranus is a planet that is tipped on its side. And so if this fist here is the sun, and I've got Uranus over here, and its axis is pointed toward the sun, then it rotates like this. And so regardless of the time of day on Uranus, if you're on that side where my tip of my finger is at, it's technically daytime. And then as Uranus makes a slow path around the sun, then you can get a change in seasons, but it takes a long, long time. It takes about 84 years for Uranus to make one path all the way around the sun. So a season is about 20 years, whereas a season here on Earth is a handful of months. So there's some differences there. And because this side of Uranus is pointed toward the sun right now for a pretty long period of time, we're seeing more energy in here that's coming out in this infrared image. So that's why this side is a bit brighter in infrared than the right side, where it looks a little bit darker. Here's just another image of Uranus. Got some little spots in here representing weather systems, a brighter side, a darker side, the up and down rings. That's your standard view of Uranus when you look at it in infrared. So let's not use all of our time on Uranus. Let's move over into Neptune. And again, I said it before, but I always find Neptune, any image of Neptune is just this beautiful image. I love this color of blue right here. And you can already see some features that you can't see in Uranus. Right now in this image, you have this darker spot right in here. And we're going to zoom in a second on that. You've got some wispy, sort of white streaks in there representing some cloud patterns. And you've got some differences in the brightness of blue too, as you go from the equatorial regions upward toward the poles on Neptune. This spot right here, which I'll zoom in on. So this spot right here is what's called the Great Dark Spot. And it's called the Great Dark Spot because it's a darker spot on the atmospheric surface of Neptune. It's a darker blue than the surrounding brighter blue. So given the creativity of astronomers, it was called the Great Dark Spot. Now, this is a spot that was first observed on the surface of Neptune when the Voyager spacecraft, again, mid to late 1980s, flew by, took our very first close-up pictures of Neptune, sent those back to Earth. Later, when Neptune was looked at with the Hubble Space Telescope, mid 1990s or so, they looked at it and this spot wasn't there. Other spots have appeared and other spots have disappeared over time. But what was originally viewed as the Great Dark Spot had dissipated and had disappeared. So this is telling us that these circulation systems, these storm patterns that we see on the surface of Uranus, on the surface of Neptune, and the same would be true for Jupiter and Saturn, that these are storms that come and go. Now, they may not come and go in a matter of days that we have for a hurricane system on Earth, or a matter of hours for some other weather systems on Earth. For example, the Great Red Spot on Jupiter, which you would have already heard about, is a big storm system that was there when Galileo first looked at Jupiter with a telescope over 400 years ago, and is still there today. There's been some changes in the size, but it's a storm system that's lasted at least 4 centuries. So we don't know how long that one will last, but we know by looking at some of these storm systems on the other planets like Neptune here, that they come and go, just like storms come and go on Earth. I put a little note on the wind speeds around in here. So measured wind speeds around a storm like this are on the order of 1,500 miles per hour. So again, I'm complaining about how strong the wind is when it's 20, 25 miles per hour. Imagine how much I would be complaining if I'm near this and I've got wind speeds of 1,500 miles per hour. I'm complaining a lot. I'm probably not doing very well either with wind speeds that are that high. So very different than what we see on Earth. This is another look at Neptune more recently. So the spot that's being pointed to in this image is not the Great Dark Spot. This is just another dark spot on Neptune. You can see the date here of May 16th, 2016 with the Hubble Space Telescope. So again, it's just showing that these storms will come and go. This one has some other features in here where on this image they've pointed to kind of some bright companion clouds, a darker vortex that's shown again down here in the bottom right image. So it's just kind of showing you that there are differences. These are complicated systems, just like weather systems on Earth are complicated systems. And being able to learn more about these systems tells us more about what's going on with these planets. It gives us more knowledge. But the knowledge that we gain from here can also be applied to weather systems on Earth. It doesn't just help us learn about Neptune, it helps us learn more about all weather systems, including those on Earth. Another image that is highlighting all of the different weather systems that are on Neptune at the time of this image. And so there's always several that are on there. There's some huge ones up in here. I mean, we are talking Earth-sized systems at this point for something like this. So think about the images that you might have seen of hurricanes on Earth. They look really large on an Earth image, but now we're talking something that would be the entire size of the Earth. So with Neptune being a much, much larger planet than Earth, you know, we have storms that are going to be much, much larger than Earth. Now this image, let me caution you a little bit. I've chosen this image because I think it's a real cool image, but it's not a real image of Neptune. It's an artist's conception of Neptune's great dark spot. And I like this image, even though it's not a real image, because this artist has, picked out the dark feature here with the great dark spot, put in some sort of wispy cloud features that we see in some of those original images of the great dark spot. The very, very nice blue color in here is really cool. So, this isn't a real image. I've chosen it because it just strikes me as just this beautiful image that if I had it as a print, it would be hanging up on my wall here at home or hanging up in my office at work. But I'm kind of showing this because we have this blue color, right? Uranus is blue, kind of a pale blue. Neptune, a much darker blue. But why do these two planets look bluish in color? Like, what's going on with them in their atmospheres that give off this blue color? Because Uranus and Neptune are very similar to Jupiter and Saturn in that their atmospheric compositions are primarily hydrogen and helium gas. So very different on Earth. So think about Earth's atmosphere. Earth's atmosphere has a lot of oxygen in it. We as humans need oxygen to breathe. So when we're breathing in, we are taking oxygen that our bodies then use and can exhale as carbon dioxide. Most of Earth's atmosphere is actually nitrogen. Oxygen's a pretty large component too, and then there's trace amounts of those other things. So when we get to Neptune and Uranus, you've got hydrogen and helium filling up a lot of the atmosphere, most of the atmosphere, but then you have trace things of other stuff. And those trace amounts of other stuff are really important. Even though they're not making up a majority of the atmosphere, they're very important. Here on Earth, carbon dioxide does not make up a large component of Earth's atmosphere, but it plays a very large role in the greenhouse effect. So in Neptune and Uranus, one of the other trace amounts of other stuff is methane. And so methane is a gas. It's a carbon atom with 4 hydrogen atoms. We have methane here on Earth. Methane is a pretty strong greenhouse gas on Earth, and small amounts can cause great increases in our temperature. And it's something that we are definitely worried about on Earth as we look at climate change now and moving into the future. On methane, though, or excuse me, on Uranus and Neptune, though, this methane is what gives that blue color. So methane is a gas that is absorbing a lot of the red and orange and some of the yellows and things like that into the atmosphere, and then it reflects back out blue light. And when we look at a planet, what we are seeing is the light that is reflected back out. And so if it's blue light that's being reflected back out from the atmosphere, then what our eyes are going to pick up and what a telescope will pick up is a lot of blue light. And so there just happens to be the right atmospheric composition that, particularly with Neptune, we get this beautiful blue color that comes back at us. A few weather facts for Neptune here. Again, temperatures are about the same as Uranus, and right, you'll notice that the temperature that I have here, and I looked this up to verify, but before today, is a little bit warmer than the temperature for Uranus. Uranus is negative 365. Neptune, here in the atmosphere, we have measured temperatures of negative 345. Still extremely cold. I mean, that 20 degrees warmer is not going to make it seem like a summer day. This is still very, very cold. But, differences in the atmosphere can result in different temperature measurements. So, we don't want to, don't take too much into thinking that Neptune's a warmer planet. It's still very cold. It's still receiving far less sunlight than Earth receives. It's receiving far less energy from the sun than Earth receives. Wind speeds, again, you've got wind speeds just like Uranus, several hundred miles an hour, even higher in the storms. So if you're in that atmosphere, if you took a spacecraft and you're in that atmosphere, you'd better have a spacecraft that can handle those wind speeds. Otherwise, you're going to find yourself in trouble very, very fast. The bands, we've got some, if you look closely at these images, you've got horizontal lines going across of different shades of blue. These, again, like Jupiter, like Saturn, like Uranus, are regions of rising gas. Warmer gas rises, cooler gas falls. That's what you have going on in these bands on here. So not all that different from any of the other gas planets. And then I kind of want to end here, or get close to ending here, with seasons. Again, Neptune is a planet, moves around the sun, and has an orbital tilt of a few degrees. Remember, Uranus was sort of tipped on its side, like this. Neptune is back to not straight up and down, but is more up and down with a slight angle in its tilt right there. And so, like the other planets that have a tilt, what it means is as it goes around the sun, that axis is pointed in different directions, or pointed in different directions relative to the sun. And so when it's pointed to the sun, that part of it gets a little bit more energy than the part of the planet that's pointed away. And if you've got a little bit more energy, then you have most likely slightly higher temperatures, and you have what we call a summer season. The opposite then is that area that's getting a little bit less energy, a little bit lower temperature. That's where we're going to have a winter season. Now, again, it's not like summer on Neptune is going to be a nice summer day like today here in Indiana. It's not like winter is going to be a snowy day of 0 degrees Fahrenheit. We are talking about a planet that is 30 times farther away from the sun than Earth is. So to us as humans, it's just cold. It is just cold all the time. But these images here, 1996, 1998, 2002, are just showing you the differences in infrared radiation being emitted. So we got just some differences on one part of the planet compared to the other. And again, that's showing us which parts of the planet are receiving more energy from the sun and then releasing it back out at this current point in Neptune's orbit around the sun. Now, 1996 to 98 to 2002, that's a span of 6 years. So on Earth, we would have had 6 summers, 6 springs, 6 falls, 6 winters. Not the case on Neptune. Neptune takes about 160 years to go all the way around. 160 years to go all the way around, meaning that a season is roughly taking 40 years. So if I lived on Neptune, then my entire life has basically been one season. So if I was born at the start of summer, then where I'm at in my life right now on Neptune, we're finally getting out of summer and we're moving into what would be called Neptune's fall. I hope I do, but I might make it to Neptune's start of winter. But I will not make it to Neptune's end of winter. I will not make it to 120 years. At least I don't think I will. So when we talk about seasons, they're very long. Again, you've got 40-year seasons approximately on Neptune. So very different than what we have on Earth, but similar to what's going on with Uranus and the other gas giants. And so with that, I have the ends of this presentation. I've left some time. We've gone about a half an hour here. So if there's questions and you haven't typed those in, go ahead, type those in, and Dana will ask me.
Thank you so much, Dain. That was really informative, and it was really interesting to hear all about the differences between Uranus and Neptune and the other planets in our solar system. I'm going to go ahead and stop sharing your screen so that we can get into the questions that are coming through the chat here. So Robin Copeland wants to know, do we have any idea why Uranus is so different in regards to how it spins? And I've always been told that it's maybe due to a collision early on that kind of forced it onto its side. But do you know anything in addition to that, or any other?
Yeah, I mean, yeah, I mean, and that is a very good question, because if you see something that's odd in the solar system, where in this case Uranus is tipped on its side, then a question you should ask yourself is, well, why? So I'm excited that that question was asked. And when we look at the solar system, there's always the things that kind of follow a normal pattern, and then there's some things that don't follow a normal pattern. And the general rule of thumb that I kind of give my students in class is that if we're talking about things in the solar system, generally the best explanation is that something that doesn't follow the pattern is due to a large collision early on in the solar system. So early on in the solar system, at the sun forms, you don't have the 8 planets. You've got a lot of stuff that's collecting to form planets. Things will collide with each other, and every collision where there's a transfer of energy can do something. I mean, it could potentially destroy something if it's smaller. Probably what has happened with Uranus is something very large, a planet-sized object, struck it and caused its tilt to change. Now, there's still a lot, there's always a lot of research that's going on. We'll never be able to go back in time here to see an impact, unfortunately. But there are a number of astronomers who are building models based on the things that we know, computer models that will go backwards in time to see, could Uranus be tipped on its side like that if another object of these conditions hit it just right? So, we still probably look at that large impacts as the thing that caused oddities like Uranus being tipped on its side.
Yeah, we really need those computer simulations because we can't easily recreate that, or really ever recreate those kind of conditions in a laboratory.
I mean, we can look back in time. I mean, when we're looking at telescopes, we look back in time. If we're looking with the Hubble Space Telescope at an object that's well, let's just say we're looking at something that's many light years away. That's light that left that object many years ago. So we're kind of looking back in time there, but we can't do that in our solar system.
Yeah, and it's hard to see things really small. Like it's very, very difficult to see the small planets outside of our own solar system and in earlier stages of formation.
Exactly.
Yeah. It's interesting though, because, Uranus and Neptune are more of like gases, or they have ices. It's not really a solid surface. So it's interesting to think about a object colliding with those planets and actually having an impact on the tilt, given that they're really colliding with mostly atmosphere. So how does that really change to that drastic of a 90-degree tilt? You know what I mean?
Yeah. And there are things that, and I can't give you the answer, right? I'm not the astronomer building the models. It wasn't my area of expertise in grad school, but the thing is that if it was something small that strikes Uranus, then nothing really happens. I mean, we have small things like comets that strike these outer planets at different times. There's some really cool images that have been taken after a comet that broke apart. The different pieces struck the atmosphere of Jupiter, and you can see the temporary sort of leftover marks in the atmosphere of Jupiter. And so there's similar things like that, but it doesn't change anything really with the planets. You have to have something really big, and early in the solar system there was that material where that could happen. Like today, that's not going to happen today in our lifetimes, because you've got the planets, and it's not that something can't change the orbit of a planet, but you'd have to have something coming from outside our solar system in, like a rogue planet or something. And I don't know if that's a topic that's ever been discussed in this series, but there is this idea of rogue planets that got kicked out of their solar system. They're floating freely through space, and there's that very, very, very small chance they could enter our solar system. And if they did, there could be an effect there.
Yeah, we haven't talked about rogue planets entering our solar system. We have talked about a rogue comet, though, entering our solar system just a few months ago.
Yeah.
Yeah. So Tony wants to know, what is your favorite planet and why?
um, what is my favorite planet and why? You know, this is hard. I mean, one, I do really like Earth. I like living here. I like having, you know, the conveniences of everything around me on Earth. Even in a world of COVID-19, where I have to be cautious about where I go and wear my mask when I go out there. It's really easy to go get supplies. um, I think it would be cool. I mean, I love Mars. I mean, there's so much that's really interesting about Mars. That reddish color, the evidence that is pointed back to liquid water on the surface makes it really cool.
Yeah.
Um, so if I'm going to pick a favorite planet, I'm going to pick Earth as number one, and then I'm going to do Mars as a close second. I do love that dark blue color of Neptune, though. So,
Yeah.
if I
I have
really rank
found
them, maybe Neptune comes in third.
Yeah, you got to rank them. And I think that ranking changes over time. I
Oh
found
yeah.
that my favorite planet is usually the one I am studying that week, because the more you know about something, the more interested
Mhm.
you become in it and the more you fall in love with it. So I found that when I'm doing a presentation on Jupiter, Jupiter is my favorite planet that week. And so it changes every week, every month. Uh,
Yep. Yep. It's the thing that's on your mind, and you're
yeah.
learning new things, and that's exciting.
Exactly. So Michelle is asking a question that I actually was going to ask about. We haven't visited Uranus and Neptune with a spacecraft since the 1980s, and that was the Voyager 2 spacecraft that saw them. We actually have since then sent the New Horizons spacecraft to explore Pluto, and we have better pictures of Pluto now than we do
Mhm.
of Uranus and Neptune, which is kind of weird to think about, but it's true. And so, are there any missions that are being planned to explore Uranus and Neptune again? Do you know?
Oh, that's a good question. And um, off the top of my head, I'm not aware of any. Now, that doesn't mean that there's not some longer term plans out there, or
Hmm.
there's something that I just haven't heard of. I mean, NASA is planning missions all the time, and NASA is not the only space agency on Earth. Um, but NASA's planning new missions all the time, looking out at potentially 20, 30 years in the future in some cases. So I would urge you to, and I would have to do this too, is to look at, and you go to NASA and look at missions, and go to the NASA website, and they've got a missions page there, and look at future
Hmm.
missions. And there's a whole bunch of them. I mean, there's a
Yeah.
tremendous number that are out there. So I don't always keep track of all of them. Um,
Because there's a lot in planning, and then there's some that have been approved and are still in more
and
planning.
and there's a
The
lot of
process.
missions where planning happens, and planning happens for years, and then you get closer, and then something gets canceled because of funding reasons, or funding priorities get shifted.
Yeah.
There's only so much money, right? And so you've got to choose your priorities. And so we have a lot of stuff that's always going on with Mars, and part of that is we can get a rover to Mars. The other part of spending money on Mars is that this is a planet that had similarities to Earth, and has a lot of evidence there was liquid water on the surface. So, I know that astronomers would love to study Uranus and Neptune more.
Yeah.
Would love to send another spacecraft out there more. Maybe it's something that goes into orbit. Um,
Exactly, because we already did the first step. Because usually what we do is we send a flyby mission, and that was Voyager 2 in the 1980s, like I said. So we already did that first step.
yep.
And now we can send maybe something to go in orbit, like you said.
And the other interesting thing about these two planets is it's not just the two planets. If you send a mission that you orbit, you've got now the potential to study some of the moons that are out
Exactly.
there. Um, there's much more going on with moons than there was, say, 20 years ago.
Hmm.
We've got a lot of evidence of ice or liquid water below a surface on a moon. There's a moon that's got geysers that can shoot stuff up.
Yeah.
Neptune has a big moon called Triton that I think you're going to be talking about in the future. So there's a lot of cool stuff with moons. I mean, set the two planets aside. There's a tremendous amount of cool stuff with just the moon. So
exactly.
So I have to answer that question with I don't know, but it's not something that immediately strikes me as recognizing that there's a dedicated mission that's close to ready for Uranus and Neptune. But there could be something in the planning stages.
All right. So Mark wants to know, I think Mark used to be a student of yours because he said it's nice to be in your astronomy again. But he also wants to know an easy way to prove the Earth is round.
an easy way to prove the Earth is round. Yes, because here's where we get into the flat Earth theories. And right, I can go out and I can, I look out my window and stuff, and Earth certainly appears to be flat. And I don't see myself moving. I don't feel myself moving and rotating. So, it's hard. I mean, I can understand, particularly going back hundreds of years ago without the scientific, understanding that we have today. It would make sense to think that Earth is flat because the experiences show that it's flat. But there were science experiments going back several hundred years or more that were making measurements and determining that the Earth is not flat, that it is round. I mean, there's a number of pieces of evidence that you can use to point to that. And I may have the person wrong. But I think it was a Greek astronomer, Eratosthenes. Okay. Who made measurements of shadow lengths at different locations on Earth. And from those shadows was able to work through some of the geometry to show not only that Earth is round, but to then extrapolate to get an overall circumference of the Earth. So at this time, nobody can actually measure and walk around the Earth that can't do that. But from two locations can get a circumference showing that it's round, but also getting something that was relatively accurate for what we know as a circumference today. I mean, the easiest way is we have all of these images, right? That NASA has put together showing a globe for an Earth, showing that things are round. We know that the moon is round. We can see it. We know the sun is round. We see a curved shadow during eclipses, whether it's for a lunar eclipse, that's Earth shadow onto the moon. It's curved. Mm-hmm. So all of this points to a round Earth.
And that experiment that you mentioned was actually, it looks like it was done in 250 BC, so not hundreds of years.
Oh, yeah. Okay. So now we're 1,000 years ago.
Yeah.
Yes. I knew it was early. I just
hundreds and hundreds. Yeah.
But you'd have to conclude that all of this evidence is being manufactured for some nefarious purpose that I don't know what it would be.
It's a big lie to put out there, and I don't know if humanity could keep that kind of a secret.
No, we are not good at keeping secrets.
Right.
I mean, two people have a hard time keeping a secret, let alone the thousands that work at all the facilities at NASA, for example. No secret is being kept. I can guarantee it.
All right. So going back to Uranus and Neptune, there's some other questions that we'll get to in the chat about some other topics, but I want to bring us back to Uranus and Neptune for a second, but then also put it in the context of our lives right now with COVID-19. So we looked at a lot of infrared images of Uranus and Neptune, and we've been seeing those touchless infrared thermometers a lot lately. And I've been wondering that whether or not those are giving an accurate internal temperature reading, and if you knew anything about that. I know it's a difficult question and I've been asking it for a while, but no one seems to know the answer.
I don't know. I would be skeptical, and when I say I would be skeptical, it doesn't mean that I don't believe it. It means that I would have to, I'd have to know more about the manufacturer that is making these.
It says that they have to be FDA approved, but it's still taking a reading of your surface temperature, like your body temperature, not an
Yeah.
internal temperature.
And so off the top of my head, I mean, right, I have a little infrared device. We were
Hmm.
using it for some science experiments with my kids a couple of years ago, so I could point it to different things and would read it. It would give a temperature.
Yeah.
And I would point it, at them, like at a forehead, for example, and would it read 98.6 degrees Fahrenheit? No.
No.
It's reading
Yeah.
it's reading lower than that because it's not an internal temperature. It's reading the temperature of the or what's being emitted right there. So
Yeah.
um,
But maybe it like offers a baseline and
it could offer a baseline,
yeah.
and there's probably some extrapolation where it's taking an external temperature and then does something with that number to link it then to a more accurate internal temperature.
Oh, I see.
That's my guess. I mean,
Yeah.
I don't know for sure. I'm just kind of guessing.
Okay. Well, these are very difficult questions, so I'm glad that we have
No,
some
yeah.
ideas though of what's
I'm
going
telling you
on.
right now, I do not know everything, and in the answer, I don't know is a powerful answer, and
It is,
it's
yeah.
something that like a message here that I would send out to everybody. Don't be afraid to say I don't know.
Yeah.
I don't know means that you don't know, but now you have an opportunity to go learn more. And so
Yeah.
I'm probably going to look up a little more on these temperature these temperature
Yeah.
reading things because I don't know. I
Yeah,
just
because
don't
now the
know.
question's there and you have to answer that question. Yeah. That's what scientists do. That's what science is all about, is
Yeah.
answering questions. And so
Yep.
it's really exciting actually to not know something, because then you get to ask those questions and try to find the answer.
Exactly.
So Robin says that the temperature taker at work the other day said that she was, or they were 91 degrees. So they thought that that was quite high. All right. So another question comes from Tony. Since Earth is your favorite planet, how can we convince others, especially our nation's leaders, to care more about climate change? And one of the things from Catherine Hayhoe, actually, who talks a lot about climate change, she says one of the most powerful things we can do is to talk about it.
Mm-hmm.
But do you have something else that you would add to that?
Yeah. I love Catherine Hayhoe. Follow her on Twitter, and there's always all sorts of. I mean, she's always posting.
And she came to speak at Ball State just a
And
few years
yes,
ago.
a couple years ago, and I saw her. Very very wonderful. The work that she does is a great contribution to society. It's yes, you have to talk about it. It's but it's also the way you talk about it, because if you are, if I'm approaching somebody who, for example, doesn't believe that Earth is warming, or believes that it's warming, but humans have nothing to do with it, and therefore we shouldn't be making policies that are changing how we live. It's not enough. It's almost never enough to just state the facts, because too often the other person will. I mean, they're ingrained in their own. We all have biases, right? And it's natural for us to kind of fight back against something that is being told to us that doesn't match what we think is the truth.
Mm-hmm.
And so people naturally kind of fight against that. But with climate change, I think one of the things that helps is, one, having a kind of an open and honest conversation, but not getting mad at the other person, right?
Yeah.
If you're just going to get mad at them and call them a denier, or tell them that they're believing in fake news and fake science and things like that, then they shut down.
Yeah.
So it's about being sympathetic. It's about showing empathy to the other person. It's about trying to meet them in the middle. A lot of times, if you can talk about climate change and the way that it's impacting humanity now, to show the different ways that, like this region of the globe is having water shortages because the seasons are changing in different ways. Like the rainy season is now longer and there's more flooding, and so crops are being destroyed. If you can look at the effect that it has on humans and like observable effects, then that can be a way to kind of reach. But it's also just understanding that you probably are not going to reach that person in one conversation. That it takes kind of a long time, and that's kind of why Dr. Hayhoe is always pushing, continue to talk about it.
Right.
People's minds do change. I mean, there have been things that that I know myself, that I've had biases on, that I heard something else and I'm like, no, that is absolutely not true at all. I know that I'm right. Only to later find out, wait a second, I wasn't right.
Yeah.
And when you're not right on something, you've got to be able to own up to that. And then that's hard. I mean, it is hard recognizing you're not right on something. And
there's some humility there. And
yeah.
So I've heard from science educators that getting them to come to your point of view or to agree with you isn't the win. Having the conversation is the win. So having these conversations over time is just as important as getting maybe someone to agree with you on something.
Yeah.
And then maybe you'll learn more yourself too, right?
Exactly. I mean, anytime people are debating, I mean, we think of debates more in political debates, but even conversations among scientists at conferences where they may disagree on something, it's not so much about those two individuals. There's also an audience there too. And so what you're saying could have an impact on audience members.
Yeah.
The conversation is the
exactly
thing.
Yeah. So it's not always about who you're speaking to directly, but maybe who else is in the room, who might be on the fence, more of a neutral audience who is trying to really figure out these answers themselves. And so they're really paying attention to the conversations on the side, trying to figure it out. We do have a question from Robin. She wants to know, she said, I know earlier in the presentation you mentioned that learning about the weather systems on other planets help us learn about our own. Can you give us an example of something we've learned about Earth by studying other planets' weather systems?
Example on Earth? I think that's a good question, and I don't know if I'm going to be able to pull a specific example, particularly linked to Uranus and Neptune. Now I know with Mars, for example, we've done a lot in trying to study the weather of Mars. Mars, of course, has a much thinner atmosphere, but there's enough stuff in the atmosphere that you get these huge dust storms that sweep across the planets, and things like that. So that there is knowledge that we can take away from measuring things like wind speed, how large a storm might be. Like Mars, for example, can have dust storms that can sweep across and cover half the planet or potentially even the entire planet at a given time, much larger than things on Earth. But what it allows us to do is, by taking these measurements with different atmospheric conditions. So Mars has a much thinner atmosphere. We can make kind of comparisons on Earth, and that could help us understand a little bit why maybe we don't have dust storms that sweep across the entire planet. Actually, I should be careful on that last statement, because the last week ago there was the news about
from Africa,
the dust from the Sahara Desert was now covering the United States. But let's just say we don't see those necessarily as frequent. So it's the data that we can get when we do these measurements that we can add to the pool of everything else we have, that can help with the building of models that we have. Everybody likes to talk all the time about, don't listen to the weather forecast. It's always going to be wrong, and things like that. But if you compare the weather forecasts that we have now in 2020, their accuracy at 3 days out and 5 days out is much, much better than it was 30 years ago, in 1990. What we pick up as humans is just, well, there was a miss, and so we're going to remember the miss. But every piece of data that we have, whether it's with Earth or whether we're learning new things about weather on Mars in different conditions, is data that can be used in enhancing and improving the models that we have here on Earth. And we want to do that. I mean, on Earth, we don't think of a weather forecast of whether it's going to be 90 degrees or 95 degrees necessarily being all that important, but there are areas where it's life and death. When we look at better hurricane models on predictions there, or tornado conditions, and getting news out to people, warnings out to people as quick as possible, those are life and death type of things. So any improvements that we can make there with other data is always a benefit.
Yeah, absolutely. So I'm sure we could talk for another 30 minutes,
Probably
but
could.
I do want to respect your time and everyone else's time. So if anyone is watching this later and has a question, feel free to put it in the comments and we will try to get the answers to you as soon as we can. But thank you so much, Dr. Kavars, for joining us today, and it's been a pleasure.
Yes, yes. Thank you for having me. It's been a lot of fun.
All right, everyone. So as we wrap up here, let's go ahead and introduce the next topic that we're going to be exploring for the Your Universe series. We're going to be talking about Pluto, not just Pluto though, the moons that it has, as well as the other objects in what's known as the Kuiper Belt next week. And we're going to have a presentation on July 10th with a lot of faculty and staff from our Department of Physics and Astronomy, which the planetarium is a part of here at Ball State. Well, thanks again, everyone, for watching. Have a great weekend. Take care.